those number systems we have, like binary, octal, hexadecimal, decimal we have, right? Yes. So I hope you have got a clear idea about all this. And if you already know them, and I hope you have got a brush up about that particular concepts, right? Now, so let me share my screen, and please confirm me whether my screen is visible. 1 minute. Let me on this. Yes, yes. Thanks for confirming. Yeah. So this is the VLSI RTL design and verification batch, which is going to start from 3rd February 2025, and you have top 20% performance job guarantee and job assistance from for remaining 80% candidates, and guarantee internship opportunities also present at the Kalki Tech. So it is going to start from 3rd February 2025. You can register here by contacting these two numbers. Any one of this number you can contact them. Okay. So this was about the VLSA RTL design and verification batch. So we will start with the topic called complements in numbers. So yeah. So let us see what are these complements in numbers. So complements are used in arithmetic operations, particularly subtraction, and are essential in digital systems for, for simplifying operations like subtractions. Like if we want to subtract any numbers, any two numbers, instead of subtracting them, we are using this particular concept of complements. Okay, so we are performing this complement operation on a particular number, and we are going to add those. Let's say suppose if we want to subtract this two numbers a and b, let's say these two are binary numbers. If we want to subtract these two numbers a and b, which are binary numbers, then instead of subtracting them directly, what we are going to do is we are just performing one's complement on this particular number b. That is a plus one's complement of b, or you can also perform a plus two's complement of b. Okay, so instead of subtracting the numbers directly, you are going to add them using this particular help of this complements. Okay, so is it clear? The basic use case of complements, is it clear? Yes, everyone, is it clear? Yes. Now, so complements are also we have different type of complements in our number systems. Let's see one by one. So there are two type of complements actually. One is R's complement and another is R minus one's complement. So R's complement is also known as base complement, and R minus one's complement is known as diminished radix complement. Okay, so where R is the base of the particular number system. We have different number systems, right? So for octal number systems, how many type of complements we have? R's and R minus one's complement. So what are all the complements we have for an octal number? Anyone? So for an octal number, yes, 8 and 7's complement. Okay, yes, 8 and 7's complement. So for an octal number, we have 8's complement and 7's complement. Okay, and for a hexadecimal number, we have 16's complement and 15's complement. Like this, for different numbers, for decimal, we have tens and nines, and for binary, we have two's complement and one's complement. So basically, we have two type of complements. One is R's complement, and another is R minus one's complement. R's complement and R minus one's complement. Right now. So let us start with the ones and twos complement in binary number system. So for binary number system, the radix or the base is R is equal to 2. So that's why we have two type of complements. One is R minus one's complement, and another is R's complement. R minus one's complement and R's complement. Okay. So in binary number system, the ones complement of a number is obtained by flipping all the bits, that is changing ones to zeros and zeros to ones. And ones complement, this is one of the formula. You can perform this flipping, or you can perform this formula r power n minus 1 minus r power n minus 1 minus n, where r is a base and n is the number of bits used to represent that particular number, and n is that particular number. Okay, you can follow this, or you can simply follow this method, changing ones to zeros and zeros to ones. That's it. You can follow anything. Okay, So we'll follow the basic method which is given here. So let's say if we have a number triple one. So what is the decimal equivalent for this triple one? 7. And simply if you want to perform one's complement, then what may be our answer? What is the one's complement on triple? Yes, very good. Correct. Okay. And if you want to try to use this particular formula, this is 7, right? So if you want to use this particular formula, what we can do? R is a base rate, 2. And how many bits are required to represent this particular number 7? 3 minus 1 minus number 7. Okay. 2 power 3, 8 minus 1 minus 7, which is nothing but 0. Okay. You can either use this formula or you can either use the flipping method. Okay. So is it clear for everyone? The one's complement, is it clear for everyone? If it is clear, please acknowledge. Yes, yes. Now, so this is one more example. Like if we have 0 1 1 0, if we want to perform one's complement of this particular number, we will simply perform one's complement using flipping all the bits 1 0 0 1. So this is a one's complement of this particular number 0 1 1 0. Okay, so this was about your one's complement. Now coming to two's complement, that is R's. Okay, so for binary, that is base 2, we have R's complement, that is 2's complement. Okay, so let's see how we are performing this 2's complement. 2's complement is nothing but one of the formula is R power n minus n, or you can also perform 2's complement by doing 1's complement plus 1. Okay, so one way is to perform R power n minus n, and another way you can follow is 1's complement plus 1. Okay, let's say suppose if you want to perform 2's complement on triple one. Okay, then first perform one's complement on this particular number, that is nothing but 0 0 0, then add 1 at the LSB, that is here. Then what will be our answer? 0 0 1. So this is the 2's complement of triple one. Okay, so is it clear for everyone? Yes, correct. Let's say suppose if we have 0 1 1 0. Okay, if we want to perform 2's complement on this particular number, then what will be our answer? My question is 0 1 1 0. If I want to perform 2's complement on this particular number, then what is my answer? Yes. Right? Yes, correct. Now, and same for octal numbers, my R is nothing but 8. So how many complements we have? R's complement and R minus 1's complement. So for octal numbers, we have 8's complement and 8 minus 1, that is 7's complement. So we have two types of complements for the in the case of octal numbers, that is 8's complement and 7's complement. So let's see first 7's complement. The formula is R power n minus 1 minus n. This is the same formula. Or you can simply subtract 7 from each digit. Okay, so that is another way. You can simply subtract 7 from each digit, or you can follow this particular formula which we have already discussed in our previous slide. Let's say suppose if we have 3, 2, 5 to the base 8 in octal. If you want to perform 7's complement, then what we are going to do? We are going to subtract 7 from each digit. Okay, 7, 7, 7, 3, 2, 5. Then 7 minus 5 is 2, 7 minus 2 is 5, 7 minus 3 is 4. So 4, 5, 2 is our 7's complement of 3 to 5. Is it clear for everyone? Yes? So how to perform 7's complement, is it clear for everyone? Yes. Others, is it clear? Yes. So what is the 7's complement of 405 to the base 8? I think you can all do it, right? 405 to the base 8. Yes. Okay. Simple subtraction. Yes. And coming to R's complement, that is 8's complement in octal. So we will first perform 7's complement. For performing the 8's complement, first we should perform 7's complement on this particular number. Then we are going to add 1 to that particular number. Let's say this 3 to 5. What we are going to do? What is the 8's complement of this particular 3 to 5? What is the 8's complement of 3 to 5? 8's complement of 3 to 5. Correct? Yes. Just add 1 after performing 7's complement. Okay. Then you will get 8's complement. Okay. Yes. Correct. So this was about your octal 7's and 8's complement. Similarly, you can perform 15's and 16's complement, and you can also perform 9's and 10's complement. I hope all of you can perform right. Anyone need assistance in this particular case? Sevens and sorry, hexadecimal, 14s and 15s complement and 9s and 10s complement. Anyone need any example regarding this, or shall we move forward? Yes, if we have a particular base number, then we will have that particular r's and r minus 1 complement. So that's why I have simplified in the starting only. We have r's complement and r minus 1 complement. Depending upon the base, we will have that particular complements. Okay. So if your number system base is 6, then you have r minus 1 complement, that is 5, and r's complement, which is nothing but 6. Okay. Is it clear for everyone? Can we move forward? Yes, is it clear for everyone? Yes. Others, is it? Yes. Yes. No. Now, so when we are representing our binary numbers, we have actually three forms of representation. So when we are representing our binary numbers, we have three forms of representation. One is sign magnitude form, and another is ones complement form, and followed by 2's complement form. I'm talking about binary numbers. Okay, let's concentrate about this binary numbers, because why we are only focusing upon binary numbers, because everything in digital we are going to focus upon this particular binary only. Okay, so your computer language, everything is going to focus upon binary. So this binary representation is of three forms. One is sign magnitude representation, and another is one's complement representation, and two's complement representation, right? Now let's see what is meant by this sign magnitude everything. Okay, so binary numbers can represent both positive and negative values. Okay, so binary numbers can represent both positive values and negative values, and these are three commonly used methods for signed numbers in binary. So sign magnitude, one's complement, and two's complement. Okay, so what I mean by signed numbers, and what is the difference between the signed numbers and unsigned numbers? Signed, or you can say signed representation and unsigned representation. What is the difference between this? What is meant by signed and what is meant by unsigned? Yes. Others? Only few responses today? Yes, yes, yes. So signed can have, yes, signed can have both positive and negative, whereas unsigned can have only positive. Okay. So in the case of signed magnitude, let's start with the discussion of signed magnitude representation. So in the case of signed magnitude representation, the MSB has the role of representing whether the number is positive or negative. So if the MSB is 0, then the number is positive, and if MSB is 1, then the number is negative. Okay. So in the signed magnitude form of representation of a number, the MSB plays a key role for determining the whether the number is positive or whether the number is negative. Okay. Let's see an example for this. So before going to see the example for this, this is the range of an n-bit number, n-bit system. The positive range is from 0 to 2 power n minus 1 minus 1, and negative range is minus 0 to minus 2 power n minus 1 to minus 1. Okay, here we have minus 0. This we will see in the disadvantage section. So for in the case of signed magnitude representation, we have plus 0 and minus 0. There are two representations of this 0. Okay, so please remember the range. So this is the range of positive numbers, and this is the range of negative numbers. Okay, so 0 to 2 power n minus 1 minus 1, and negative numbers minus 0 to minus 2 power n minus 1 minus 1. Now, so if we want to represent plus 5, so how? So what is the signed magnitude representation of plus 5? Anyone, any answer? Why we should not do complement form signed bit? We are discussing about signed magnitude representation, right? Yes, correct. Here MSB represents a positive number followed by the magnitude. Okay, so 0 is a positive and 101 is, this is the magnitude. Okay, this is magnitude and this is sign. So that's why it is a signed magnitude form of representation of a particular number. Okay, so the MSB represents the sign and remaining part represents the magnitude. Okay, and if you want to represent minus 5, so what is the representation? So we will use 1 followed by 101. So this is my magnitude and this is my sign. Yes, yes, correct. Okay, now, so if we want to represent plus 0, how we are going to represent? Yes, and if we want to represent minus 0, can we represent minus 0 in signed magnitude representation? Yes, but yes, there is a representation of minus 0 also. But speaking practically, is there anything like minus 0? No, no, right? There is no minus 0. But using the signed magnitude representation, you can have two representations of 0, that is plus 0 as well as minus 0. Okay, so this is wrong, right? So this is the major drawback of signed magnitude representation. So in case of signed magnitude representation, you have two representations of your 0. Plus 0, you have one value, and for minus 0, you have another value. Okay, plus 0, you have 0, 0, 0, followed by minus 0, you have 1 followed by zeros. Okay, so this is the disadvantage of this. So now let's see about ones complement representation. So if we want to represent ones complement representation, so how we are going to use it? So positive numbers remains unchanged. So we are not going to perform any complement on this positive numbers, whereas negative numbers, we are going to represent them in ones complement. Okay, let's say, so negative numbers are represented as ones complement of positive number. Now let's see how we are going to represent. So before that, here also for positive ranges 0 to 2 power n minus 1 minus 1, and negative numbers minus 0 to minus 2 power n minus 1 minus 1. Okay, so how to represent minus 5? How to represent minus 5? Anyone? In ones complement represent? Yes, yes. How to represent minus 5 in one's complement representation? Yes, yes. Very good. Actually, it's very good to see that you are very strong in your digital basics. Yes, correct. Others, please try to answer. If you're facing any difficulty, please ask me. I will help you. Okay. Yes. Many of you are very strong in your digital. I can see that. Yes, very good. Yes. I hope this energy will continue till 30th day also, right? When we are discussing some advanced topics in sequential circuits, I hope it will be continued. Yes, yes, sure, yes. So these are the representation. For plus 5, we are not going to perform any ones complement, whereas for minus 5, we are going to perform the ones complement of this particular number 0101. Okay, so it is going to be 1010. Okay. Now, so negative numbers are easier to compute. So just we are going to flip the bits and a simpler representation than sign magnitude. Because if we want to represent plus 5 in sign magnitude representation, we need to represent this plus 5 using 0101, and for minus 5 we are going to have sign bit as 1 followed by 101. So for making this sign bit as 0 or for making this sign bit as 1, we need some extra circuit. Whereas in the case of this particular ones complement, just we will flip the bits. That's it. If we perform any XOR operation or something, our bits will be flipped and we will get the particular ones complement representation. So that is a advantage over the sign magnitude representation. But there are again two representations for 0. For plus 0 we have one representation, and for minus 0 we have another representation. Okay, so this is a disadvantage of ones complement also. Now, and there are some more disadvantages that we will see in the upcoming slides of this one's complement and sign magnitude representation. Okay, so after completing this two's complement representation, we will see that particular disadvantages also. So in the case of two's complement also, we are going to represent positive numbers unchanged, whereas negative numbers are to be converted into two's complement form. So this is a range of positive numbers, that is 0 to 2 power n minus 1 minus 1, and negative range if you see minus 2 power n minus 1 to minus 1. There is no representation of minus 0 here. Okay. So the range is from 0 to 2 power n minus 1 minus 1, and negative range is minus 2 power n minus 1 to minus 1. So if you want to represent plus 5, then you can simply write 0, 1, 0, 1, and minus 5 is nothing but 2's complement of 0101, that is 1011. So what is the 2's complement? Let's say 1010. How to find the 2's complement of 1010? One zero one zero. 2's complement of 1010. Yes, that's it. Plus 1. Okay. Now, so question arises like why we choose only 2's complement for storing the negative numbers in modern computers. So if you want to store any negative number in your hardware chip, can you directly store your negative number in your hardware chip? Whether you are going to store your negative numbers inside your hardware? No. So you should perform either one's complement or two's complement. Okay. So let's see why we are choosing two's complement over other form of representations for storing any negative number. So unlike the sign magnitude and one's complement, two's complement has only a single representation for 0. So it makes more efficient and consistent. And one more thing is two's complement has more range of representations than one's complement and sign magnitude. So two's complement has a wide range of representation compared to this one's complement and two's complement, sign magnitude representation. Okay, so that was the advantage of using two's complement in the representation of negative numbers in hardware. Now, so let us see some applications like how we are going to use this one's complement. So let's say if we have a particular number 3 minus 2. Okay. Now, so we should perform this particular subtraction using one's complement. Using one's complement. How can we subtract this? So just simply represent this 3 in normal representation, that is 0, 0, 1, 1. And this 2 is nothing but this is 0, 0, 1, 0. Now perform one's complement on this 2 because we have negative symbol on this particular 2. Okay. So what we are going to do 1, 0, 1. Sorry. It is nothing but 1, 1, 0, 1. Okay. So we have performed one's complement on this particular number and we have left it 3. We have left it as it is. Okay. Now we are going to add these two numbers 00, 11 and 1, 1, 0, 1. So what is the result we are getting? 1 plus 1 is 0, 1. 1 plus 1 is 0 carries 1. 1 plus 1 is 0 carries 1. And 1 plus 1 0 carry is 1. So if we get any carry, so we should add that end around carry. So triple zero, sorry, 4 zeros, and we are going to add that carry again. So we will get 0001. So what is the answer we are getting? If we are performing this particular operation, what is the answer we are getting? Yes, yes, yes. So is it clear how to subtract two numbers using one's complement representation? Is it clear for everyone? Are we getting the correct answer? Are we getting the correct answer? Yes. Anyone feels it's a wrong answer? And if you have any alternate answers for this? No, right? Everyone on the same track, right? Yes. Yes. Now, let's say if you have to perform -3 plus 2. Okay. If you have to perform -3 plus 2, then on which number you are going to perform one's complement? -3 plus 2. On which number you are going to perform? Yes. So we should first write 3 in its normal form, that is nothing but 0, 0, double 1. Then we should perform the ones complement on this particular number. Then we will get 1, 1, 0, 0. And 2 we will write it as it is, that is 0, 0, 1, 0. And we are going to add these two numbers 0, 1, 1, 1. Are we getting any carry? So are we getting any carry in this particular number? No. So we are not getting any carry. That means it is a negative number. Okay. And now what we should do is we should perform one's complement on this particular result again. Okay. That is 1110 is nothing but 0001. So this is the result, that is nothing but -1. So since we are not getting a carry, we should tell that it is a negative number, and we should perform one's complement on the result again. Okay, if you are not getting carry, we will perform one's complement on this particular number again. Okay, is it clear for everyone? Are we good? Yes. So let's say if we have -6 plus 4, so what is our answer? So please perform it quickly and tell me the answer. -6 plus 4. Is it positive or negative? Yes, yes. All of you got how to yes, how to perform yes, how to perform addition using one's complement. Is it clear for everyone? If you have a negative numbers, then how to perform how to perform that particular addition? Is it clear for everyone? Yes, everyone, is it clear? Yes, yes. Now let's say if we want to perform subtraction on this particular using 2's complement, let us take the same example, -3. Let's say first take +3 -2. Now, whether we are going to on which number we should perform 2's complement, on which number we should, yes. Okay, 2 is nothing but 0010. So we are going to perform one's complement on this, that is 1101 plus 1, that is 1101 111 triple 10. Okay, triple 10. So 0011 triple 10. So we should add this to 1 1, sorry, 110 1 1101 1101. So in this particular 2's complement, if we get any end around carry, we are simply going to neglect this particular carry. We are going to neglect this carry. So after neglecting, what is the answer end result we have? 1. Yes. Yes. So if we have a carry, we are going to neglect it. So we have the final answer, which is a positive number. So here in the 2's complement, if we get a carry, it is a positive number. And here the result is +1. Okay. So here if we are getting a carry, please stress on, I'm stressing on this particular points. In 2's complement, if we are getting a carry, we are just neglecting it. In the 2's complement of addition, if we are getting a carry, we are just simply neglecting it. Whereas in the case of, yeah, that is a procedure actually. Okay, that is a procedure we are following. Okay, so in the 2's complement, if we are getting a carry, we are just neglecting it. And in the ones complement, if we are getting a carry, we should add it to the resultant to get the final answer. Okay. So please remember these 2 points. I will come back to these 2 points again. Okay. Now, so if we have this minus 3 plus 2, then what we are going to do? First represent 3, 0, 0, 1, 1, and minus 3 is nothing but 1, 1, 0, 0 plus 1, that is nothing but 1, 0, 1, 1, 0, 1. Okay. 1, 1, 0, 1 and 2, that is nothing but 0, 0, 1, 0, which is 1, 1, 1, 1. So here, are we getting any carry? Are we getting any carry? No. So if we are not getting any carry, we should perform 2's complement on this particular result, and it is a negative number. If we are not getting a carry, we should again perform the 2's complement on this particular result, and it is a negative number. It indicates it's a negative number. So 1, 1, 1, 1, which is nothing but 4 zeros, and we should add 1 to get a 2's complement, that is 1, 000. So our final answer is minus 1. So is it clear for everyone? What happens if we are not getting a carry, and what happens if we get a carry in the particular in the 2's complement form of representation? Okay. So is it clear for everyone? Now, so previously I have said one statement. So in the 2's complement form of representation, if we are getting a carry, we should ignore that carry in the case of 2's complement representation. Whereas in the case of 1's complement representation, if we are getting a carry, we are going to add that carry to the resultant. Now tell me, for adding the carry, will it take extra circuitry, or for ignoring the carry, will it take extra circuitry? In which case, we need extra circuitry. Yes. So what do you prefer? So what do you prefer? Do you prefer extra circuitry, or do you prefer less circuitry? What do you prefer? Like, whether you are going to prefer extra circuitry, more circuitry, or you are going to prefer less circuitry? Okay. Why we are preferring less circuitry? What is the reason for preferring less circuitry over more circuitry? Like, what may be your reason of choosing less circuitry? Okay, cost and power. Yes, yes. Yes, volume, space, complexity. Yes, correct. So, as a VLSI engineer, you should be considering all these points: power, complexity, efficiency. Yes, very good. Actually, it's very good to see all your beautiful responses. Yes, correct. Fastness is also correct. Delay. Okay. So that's why we are going to prefer two's complement of representation rather than preferring one's complement of representation. Okay. So that's why if you see in our tools also, like in Verilog, if you are following my Verilog lectures also, in our classes also, we have seen this particular. So when we are representing our any negative number in Verilog also, if you want to store it, the tool or the compiler is going to perform the 2's complement on that particular number, and it is going to store it in the memory. Okay. So that was about your complements in number systems. I hope you have got a clear and good idea about this particular complements in number systems, right? Yeah. So that's all for this session. 1 minute. Please wait. First, I will share the attendance link. If I got, let me check. Yes, I've got it. Wait a minute. Please fill the form and you can leave the session. Okay. If you have any doubts or queries, you can stay. Please wait for a minute. Let me share the attendance form. After filling, you can leave. Okay. Thanks for joining, and it's very good to see that you're very attentive, and you have a very good, strong knowledge in the basics. It's happy to see. Wait a minute. I'm copying this link. Yeah, assignment. I'm preparing some assignments. Okay. Yeah, I told you, right? Like PPT, PDF will be shared after some time, after completing this number system concepts. Okay. So instead of sharing every day, okay. So instead of sharing every day,